Yes, good morning, students. Hope I am audible. Hello.
Yes,
Good
sir.
morning, sir.
Good morning. Good morning. Okay. S- so far, we have discussed about in the previous class we have discussed about correlation receiver and matched filter, right? So with that, I said the module 2 is completed. So let me start module 3. So basically, in module 3, we will be discussing about various digital modulation and demodulation techniques. Okay. So before I start, already you are aware what do you mean by modulation. So I expect any one of you to answer that. Is it possible to say what is modulation? Quickly, any one of you? I think those who have not interacted so far, it is a chance for them to interact because I'm asking very simple question. Yes, I expect answer from you people. I'm just asking what do you mean by modulation?
Sir, it is a process in which any of the parameters of a signal is modified, sir.
Okay, try to be specific means any of the parameters of signal means what? Which signal?
Amplitude, phase, or
Uh,
angle can be modulated, sir,
phase or
for a
angle, both
message
the same
signal.
only. No? Message signal. No, just think what you have said is right or not. Yes, yes. At least I appreciate your voluntariness to express your understanding. Fine. In the meantime, others can try. Namita, you can also think what you have spoken is correct or wrong.
So, carrier signal, sir, not message signal.
Yeah, right. Okay. At least we could correct it. Fine. So, as you said, the amplitude, frequency, and phase of the carrier signal can be varied in accordance with the message signal. That message signal is what is the yeah. Uh, so here, in case of digital modulation techniques, the message signal will be a digital one. Okay. So the message signal will be what? It is a digital one. Yeah. Hope I think slide is changed now. Yes. Is this slide is changed? Hello.
Yes, sir.
Yeah. Please. Yeah. So in case of digital modulation, what I said, the information signal will be in terms of zeros and ones. Okay. So and we are going to vary, as one of your friends said, the amplitude, the frequency, and is the phase, right? Any one of these or a combination of any of these three can be done also. Okay. So if I vary the amplitude of the means I express mathematically the carrier signal like this, right? C of t is equal to a into cosine of 2 pi fct plus 5. Okay. So in this, a is the amplitude and fc is the carrier frequency and where phi is the phase. So if I vary the amplitude of the carrier signal in accordance with the message signal, then I call it as a amplitude shift keying. Okay. In here, in a digital modulation process, we call this modulation as a switching or keying. Okay. Means we are going to switch, okay, or we say keying the amplitude, frequency, or phase of the sinusoidal carrier wave according to the digital signal. Okay, if I vary the amplitude of the carrier in accordance with the message signal, then I call it as amplitude shift keying. Okay, keeping other two parameters constant, that is carrier frequency and phase. And second thing is, if I keep the amplitude of the carrier constant, amplitude and phase, right? Only if I vary the frequency of the carrier signal in accordance with the message signal, then I call that as frequency shift keying. That is what it is called FSK in short form. Okay, the amplitude shift keying in short form we call it as ASK, right? And keeping amplitude and frequency of the carrier constant, if I vary only the phase of the carrier signal in accordance with the message signal, then we call that modulation as the phase shift keying. Okay, that we call it PSK in short. Okay, so in a nutshell, with one expression, we should be able to define all these three modulation techniques. That is ASK, FSK, and PSK in short form we say. Fine. So in case of ASK, what I said, amplitude of the carrier is varied, right, in accordance with the message signal. Means the message signal is what here, it is a digital signal, means it will be having zeros and ones. Means I transmit no signal for zero. Okay, I will be transmitting this carrier signal having certain amplitude, maybe 5 volts or like that. Okay, I will be transmitting a carrier signal for an interval of TB seconds, okay, for conveying the message bit 1. Okay, for message information bit 0, I will not be transmitting any signal. That is known as the ASK, that is amplitude shift keying. In case of frequency shift keying, what happens, I will be transmitting one carrier frequency. Let us say it is F1. Okay, maybe it is 100 kilohertz. Let us assume that. Okay, I will be transmitting 100 kilohertz sinusoidal signal for conveying the information bit is 1. Okay, I may be uh, using another frequency, say F2, which is equal to 50 kilohertz for conveying message bit 0. Okay, so here only two bits, right, 0 or 1. I will be conveying 0 by some sinusoidal signal having certain frequency. I said that is of around 50 kilohertz, just an example I'm giving. Then information bit 1 will be conveyed by transmitting a carrier signal having frequency F2, okay, which is equal to 100 kilohertz. Is that fine? Then the third case, that is phase shift keying. What I said here is the phase of the carrier signal is varied in accordance with the message signal. Means here the information bit 0 is conveyed with no phase change in the carrier signal, means with 0 degree phase shift, right? Another one means information bit 1 I can convey by having 180-degree phase shift. Means if I convey this, if I make this with 180-degree phase shift for saying it is information bit 1, then it will become what, cos of 2 pi fct plus pi, so which is nothing but minus a into cos of 2 pi fct I can write. Okay, so these are the three basic uh, digital modulation techniques, what we can say. So we start discussing about PSK. Yeah, and we call since we are, if we are going for um, just one bit of information, that is 0 or 1, that we call as a binary phase shift keying. Okay, in that again versions are there, like quadrature phase shift keying means we will be able to transmit two bits of information, two bits with one phase. It may be 0 degree, 90 degree, 180, 270 degree, or it may be 45, 135, 270, and what is in between 270 and 360? Is it possible to say? I said quadrature phase shift keying means we will be conveying the message with four phase shifts. One I said 0 degree, 90 degree, 180 degree, another is 270, right? Other way is 45, that is pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So these are possibilities, right? That is a higher version of BPSK. Then even offset QPSK, DPSK, other things are there. When we start discussing, we will try to understand what each one of them. Similarly, I said no, not only the amplitude or frequency or phase, even I can combine any any of these out of these three, any parameters can be combined to convey the information. In that sense, if I take amplitude and as well as phase to convey the information, that becomes quadrature amplitude modulation. In short, we call QAM. Okay, so I think let us consider first the BPSK, that is binary phase shift keying, and let me say how we represent this binary phase shift keying uh, mathematically. How do we express mathematically the binary phase shift keying modulated signal? And let us try to understand the waveform also. Okay, so I said no, it is a binary phase shift keying. Here, binary means digital data, right? 0 or 1. Means for 0, I will be conveying with one phase, I said, and 1 information bit 1, I will be conveying with another phase. So to understand, so this is my information bit, right? 0, 1, 1, 1, 0, 1. Just have taken an example. You can represent this binary data with any of the line codes what you have learned so far. Okay, either by using unipolar, return to 0, or non-return to 0, or polar, whatever it may be, bipolar or even Manchester. Okay, accordingly, to convey the information bit 0, what is the phase shift I'm using, and conveying the information bit 1, what is the phase shift I'm using, right? So for 1, I am using cosine of 2 pi fct. That is why I have written here cosine signal, right? Able to see this? So it starts from this point, wherever my cursor is there. It is a cosine signal, right? So it is 2 cycles, isn't it? So cosine. So I've taken a number of cycles is 2. So it is a cosine signal. And for 0, I'm taking minus cos. Means cos 2 pi fct plus pi. It can be written as minus cos 2 pi fct, right? So I'm sending information bit 0 by minus cos 2 pi fct with magnitude of root of 2 ev by tb. I will tell why you are getting this root of 2 ev by tb also. Then I'm transmitting 1 with what? uh, cosine signal, which is equal to what? Cosine of 2 pi of ct with a magnitude of root of 2 ev by tb. Okay, so this is how I represent mathematically the BPSK modulated signal. Okay, symbol 1. Okay, if I say symbol 1, I can write S1 of t, which is equal to square root of 2 ev by tb cosine of 2 pi fct. And symbol 0, I denote with S2 of t. This is a modulated signal. Okay, so which is equal to what? Square root of 2 ev by tb cosine of 2 pi fct plus pi. So cos of 2 pi fct plus pi can be written as minus, right? Square root of 2 ev by tb cos of 2 pi fct. Right? So the duration, this tb is known as the bit duration. Okay, here I have written 0, 1, 1 and all. So the duration of that bit will be tb. Okay, so 0 to t is the bit duration, and this eb, e suffix b is the energy per bit. It is energy per bit. Okay, so what is the energy per bit we are using for transmitting that signal? That is eb. And fc, you all know it is a carrier frequency. I said that it will be chosen by what? Nc by tb, where nc is fixed integer value. Okay, and here I have taken, I said the value of nc is equal to 2 because I have taken 2 cycles. Hope you are able to understand. This is 1 cycle, and from here to here another cycle, so 2 cycles. So nc is equal to 2 here, so it will be 2 by tb. Fine. And always we know the carrier frequency has to be much greater than the message signal frequency. That is why it is written fc is much greater than 1 by tb, right? So I said tb is the bit duration, means message signal duration. Okay, I said already eb is the transmitted signal energy per bit, and we know how to find the energy of a signal, right? So this is my S1 of t. I transmit S1 of t for symbol 1 and S2 of t for symbol 0, right? So how do I determine what is the energy of the signal? So what I do, I integrate this signal over the symbol duration. So that is integral 0 to tb S1 square of t into dt. right? That is how I define energy of the signal, and which is equal to what? Means this is the energy of the second signal, that is S2 of t. So which is equal to integral 0 to tb S2 square of t into dt. So just substitute what is the value of S1 of t, then you will be able to say, this is how I say the energy of the signal, right? So here I am using uh, two carrier uh, signal. They differ in phase, right? By how many degrees? 180 degree. One is cos, another one is minus cos. Okay, this is how we say about binary phase shift keying. Okay, symbol 0 will be transmitted with one phase shift, and symbol 1 will be transmitted with another phase shift. That phase shift will be of 180 degree. Okay, means I here transmit symbol 1 by cosine signal and symbol 0 by minus cosine signal. So these two signals differ by a phase shift of 180 degree. Yes, if you have any questions to ask, you can ask. I said this is the BPSK modulator signal, that is for symbol 1 I say like this, and for symbol 0 I represent mathematically like this, and the duration of the signal will be what? 0 to TB. Yes, any questions you have? Do you have any
So you
questions with
said
respect to
something
this?
about NC. Could you repeat that?
Yeah, NC is the number of cycles. That's the integer value, right? Here, NC by TB is here, no? Here, with respect to whatever the waveform I have shown here, no? That I have taken here 2 cycles. Okay, it is an integer value. See, this is one cycle, and from here to here another cycle. So 2 cycles I have taken. Okay,
Okay, sir.
yeah. Whereas FC is the carrier frequency. Okay. Yes, hope this slide is clear. So it's very basic. It starts with, right. So of course I have not shown how I represent this binary information. You all can represent, I said, no, by using any of the line code. Okay. So this is what the BPSK modulated signal what we represent. Fine. Yeah. Yes. Any questions you have with respect to this slide? Yes, my dear students, please respond. Do you have any questions
No, sir.
with respect to the slide one? No.
No,
Is it
sir.
clearly under? Okay. Yeah. Yeah. So already we know what is a signal space diagram, right? So how do I represent that BPSK signal on the signal space diagram, right? So for doing that, so I am defining the basis function. Okay, for that. So how do I define that basis function? I say it is pi 1 of t, which is equal to, I'm taking magnitude as what? Root of 2 by tb into cosine of 2 pi of ct. So this is my basis function, and I treat this as my carrier also. Okay, so root of 2 by tb cosine of 2 pi f ct is my basis function, and this basis function also exists over the interval 0 to tb. So I can express S1 of t and as well as S2 of t in terms of this basis function, right? Already I wrote in the previous slide what is S1 of t, which is equal to what? Square root of 2 EB by TB cosine of 2 pi FCT, that is for symbol 1, and for symbol 0, what I said, it is S2 of t, which is equal to minus square root of 2 EB by TB cos of 2 pi FCT, right? So if I replace square root of 2 by TB into cos of 2 pi FCT by pi 1 of t, then I can write S1 of t is equal to what? Square root of EB into pi 1 of t. Hope this is clear. And similarly, I can say S2 of t is equal to minus root EB into pi 1 of t. Okay, because I said S1 of t I have defined what? Square root of 2 EB by TB into cosine of 2 pi of ct, right? And I have defined the basis function as what? Pi 1 of t is equal to root of 2 by TB cos 2 pi of ct. So I can rewrite the equation 1, that is S1 of t, in this form, that is root EB into pi 1 of t, and S2 of t as minus root EB into pi 1 of t. Right. So I know what is S1 of t and S2 of t. I can draw the signal space diagram. So this is how I write the signal space diagram. So it means it is a vector, right? I would have shown with vector representation. Instead of showing that arrow, just we are denoting by endpoints. Okay. So I take this is S1, okay, message point S1, and means this is one dimensional, what I said, right? So for this binary phase shift keying, a signal space diagram which is one dimensional, means the number of basis function is 1, so n is equal to 1 have for these two message points. So number of message points are what? 2, right? 0 and 1. So this is S1 and this is S2. I know S1 is what? Root EB, isn't it? That is why on pi 1 of t axis this is root EB, and S2 is what? Minus root EB. So at this point I am writing minus root EB. Okay. Yes. Any doubt with respect to writing the signal space diagram?
So,
Ah,
so D12 is the distance between S1 and S2, right?
yeah.
Okay. Sir.
Yeah. D12 is the distance between two message points. So how do we find the distance? Yes. How do you find distance? This minus this, no? So root EB minus of minus root EB. It becomes root EB plus root EB, which is nothing but 2 root EB, right?
Yeah, sir.
So okay, to get still better clear picture, it is shown with the waveforms. Okay, the signal space diagram it is, right? So x-axis is pi 1 of t. So this is message point 1, that is S1 I wrote, right? So which is equal to root EB, and this is message point 2, that is S2, and its value is minus root EB. I said it will be divided into different regions. So this we call as a decision boundary. Okay, and this I call region Z1, and this one is region Z2. While discussing map rule or ML rule, right? So we have divided, we have taken their example as n is equal to 2, right? That is pi 1 of t and pi 2 of t. And I have divided that into 4 regions, Z1, Z2, Z3, and Z4. So here it is n is equal to 1, right? So I can divide this into 2 regions, that is region Z1 and region Z2. So especially this diagram is very useful for understanding how about the receiver. Okay, how the receiver will take a decision in favor of symbol 0 or symbol 1. Okay, so this is about symbol 1 and this is about symbol 0, right? Symbol 1 I represent by root EB, symbol 0 by minus root EB. Means here what type of line coding you think that is used here? Looking at this value root EB and minus root EB, I represent 1 by root EB having a magnitude of root EB, and symbol 0 having a magnitude of minus root EB. Yes, any one of you can say? Looking at the value of uh, message point, is it possible to say what type of line coding might be used to represent symbol 0 and symbol 1? I said no, variety of line codes are there. You have said unipolar, polar, bipolar, Manchester, among that, and whatever the discussions we have done so far, what is the bit duration and what is the basis function duration? Looking at those things, is it possible to say? No. Okay, at least are you able to understand this message point 1 means this is your S1 of t, right? This is a cosine signal with a magnitude of what? Square root of 2 EB by TB, is positive, right? And with the 2 cycles, I said, no, it is magnified and shown with respect to the second slide what I have shown, that waveform, right? Here it is magnified. So it is a bit duration. So minus, that is root of 2 EB by TB for positive magnitude, and this is negative, right? Minus root of 2 EB by TB. So this is about message point 1, and this is message point 2. That is, this is symbol 0 and this is symbol 1. So starts with what? Minus root of 2 EB by TB, and positive is this one. Okay, so this diagram is very useful for, I said, understanding the working of the receiver, how the receiver will take a decision in favor of whether the transmitted symbol is 0 or 1. So based on the value. So looking at this diagram, you should be able to understand what should be the value of threshold we need to keep at the receiver to take a decision. I will come to that block diagram of the BPSK generation and detection. At least, are you okay with this? Yes, I'm asking you people, are you okay with this?
Yes, sir.
Signal constellation diagram. See what all you are supposed to write about BPSK. If they ask, I think at this time you may be knowing, right? So how I started and all. So now let me take the block diagram for understanding the generation of BPSK signal. Okay.
So Manchester coding is used, right?
Oh no, man, no Manchester. Polar signaling is used.
Okay, okay, sir.
Uh, Something happened. Okay, 1 minute. I think my here polar non-return to 0 line coding is used. So in polar, we represent symbol 1 by a positive magnitude, right? Positive pulse, and symbol 0 by a negative pulse. Yes, am I audible? I think my presentation. Hello?
Yes, sir.
Yes, sir.
Yeah, I think I lost that PPT. Let me open. Yeah, till it opens, let me just repeat what I said. I said in case of binary phase shift keying, that is BPSK modulation, I said symbol 1 will be, how do we express mathematically? That is S1 of t, which is equal to root of 2 EV by TB cosine of 2 pi FCT. And the symbol 0 by what? Root of 2 EV by TB cosine of 2 pi FCT plus pi. So cos of something plus pi can be written as minus cos theta, right? So with respect to that, I can write S2 of t, which is equal to root of 2 EV by TB, root of 2 EV by TB, that is minus root of 2 EV by TB cos 2 pi FCT. Okay. And I said the signal constellation diagram. While reading the signal constellation diagram, since we have only one basis function, so which is taken on x-axis, which is written as pi 1 of t, right? And I said, how do we represent pi 1 of t, and that is S1 and S2, two message signals on the x-axis. Since one is positive value, another one is negative value, so I take some point as 0. Towards right, I am representing signal S1, and towards left side, I represent signal S2. Okay. Okay, I started discussing about the BPSK generation and detection. Let me. Yes, any questions to ask, you can ask. In the meantime, it is taking time, my PPT to open. Yes, do you have any questions? I said no, as far as whatever the equations I have written for that, the type of line coding used is polar, non-return to zero. Okay. Yes, do you have any questions to ask? It may take 1 or 2 minutes to open. Hello, don't have any questions to ask? No questions. Yes, why strength is less today? Yes, able to see my PPT? Not yet.
Yeah, we can see that.
You can see? Okay. Okay. Yeah. So this is what the block diagram of BPSK generation and detection. Okay. Yeah. Okay. So is the binary data sequence is the input, right? My information is in the form of zeros and ones. That is why I say it is a binary data sequence. So first, what I do, I pass that through the polar to polar non-return to zero encoder. Okay, means I am representing that 0 and 1 by using polar NRZ signaling, right? Then that will be multiplied, means that binary data will be multiplied by the carrier signal. So this is how I say this is a carrier signal, okay, which I represent as pi 1 of t, which is equal to root of 2 by tb cosine of 2 pi of ct. Here what I get is output of the polar NRZ encoder. For symbol 1, I will be getting plus root of AB. And for symbol 0, I will be getting minus root of EB, right? So those means when the information bit is 1, I said no, it is plus root of EB. So that will be multiplied by this one, carrier, right? That is what is we say modulation, right? So we use the product modulator. So when it is multiplied, then I can write the output of that product modulator as my binary phase shift keying signal. So which I represent as S of t. So when the input signal is binary data 1, then what I said, this carrier will be multiplied by root of EB. So with respect to that, I can say for symbol 1, the modulated BPSK modulated signal will be what, square root of 2 EB by TB cos 2 pi FCT, right? So when the input data is 0, then I represent by using polar NRZ as what, minus root EB for negative pulse, right? 0 is represented by negative pulse. That is why I represent by minus root EB. So that minus root EB into this one, root of 2 EB by TB. So it becomes minus square root of 2 EB by TB cosine of 2 pi FCT, right? So with that, what I can write for symbol 0, it will be what, S2 of t is equal to S2 of t is equal to minus root of 2 EB by TB into cos 2 pi FCT. Okay. So this is very simple to understand the BPSK generation. This is what the BPSK transmitter, what we say. Yes, any doubts with respect to this simple diagram? It is not very complicated. Simple input binary sequence will be your input signal. You pass that through a polar NRZ level encoder. Right. The moment I say polar NRZ level encoder, you are representing 1 by positive pulse and 0 by negative pulse. So with respect to that, the magnitude of the positive pulse will be what? Root EB plus root EB. The magnitude of the negative pulse will be minus root EB. So which is multiplied by a carrier signal. The carrier signal I am representing as a basis function with a magnitude of what? Root of 2 by TB into cosine of 2 pi FCT. So then I said, how do I get the BPSK signal? So this is how I transmit the BPSK signal. Okay. So this is a BPSK transmitter. Then when it is transmitted over the air, I will be receiving the signal at the receiver side. So this is what the block diagram of the receiver. So I said that the received signal will be represented by x of t. So this x of t will be equal to what I can say, s of t plus the noise. Always noise will be there in the channel, right? We consider that as an additive wide Gaussian noise channel. So with that, I can write x of t is equal to s of t plus w of t, or we say additive wide Gaussian noise. So what is this block diagram? Already you are aware, right? So there will be multiplier followed by an integrator, so which is known as the correlator, right? Since it is a coherent receiver, coherent binary PSK receiver, whatever the carrier signal I am using at the transmitter side, the same carrier signal has to be used in the receiver side also. Okay, so coherent means these two carrier frequencies, means the carrier frequency which is used at the transmitter side and the carrier frequency which we are going to use at the receiver side will be synchronized in terms of its frequency and as well as phase. Okay, that is why it is called coherent. Okay, so you all know what is the operation of this correlator. What you will get? So this x of t is multiplied by pi 1 of t, right? And which will be integrated over the symbol interval. So here my symbol or bit interval is TB. So that is why I taken 0 to TB. So output of the correlator, you all know it is a vector, right? I represent here as x1. And now I need to do the estimation, right? I need to do the estimation whether the transmitted symbol is 0 or 1. So how do I do that? For doing that, I am using a decision device. Okay, basically this decision device is what any one of you can say. Okay, before coming to that, what will be this? So basically, you know what is decision device. So it has to take a decision in favor of whether the transmitted symbol is 0 or 1. So how it takes? So it will be comparing the signal vector with respect to this threshold value. Okay, so one input to the decision device is the received signal vector, right? Another input to the decision device is a threshold value, and here I set it the threshold value is equal to 0. So is it possible to say why I set it the threshold value is equal to 0 here? Yes, my dear students, is it possible to say why I have kept the threshold value is equal to 0 here in this case? Hello?
Because if it is greater than 0, it will be 1, no, sir.
So I can understand that based on the signal space diagram, right? Signal space diagram, what I have shown in the previous slide, right? So above 0 means if the value of x1 lies above 0, that is in the region z1, then this decision device will be able to take a decision in favor of the symbol 1. Okay, and if the value of x1 lies below this threshold value, that is below 0, then this decision device can take a decision in favor of symbol 0. Okay, that is what is written here. Choose 1 if x1 is greater than 0, and choose 0 if x1 is less than 0. So how do I decide what to choose? Depending upon the value of x1, whether it is greater than 0 or less than 0. Why I choose 1 if the value of x1 is greater than 0? Because in the signal constellation diagram or signal space diagram, I came to know that if the value of x1 is greater than 0, it will be a symbol 1. Okay, if the value of x1 is less than 0, then it will be symbol 0. So this is what the BPSK receiver is, and we call this as a coherent receiver. Okay, so already this correlator function, you know. Okay, that is why I said the previous lecture, if you have given importance, if you have understood that concept, then nothing to worry about this uh, circuit diagram here, understanding and explaining the operation on your own. Okay, so that is why how important every class is because of this. If you are missing these things, then it becomes difficult to understand. Hope is it clear? Do you have any doubts with respect to this BPSK transmitter and receiver? Yes, students, please communicate. I should not ask 100 times. Do you have any questions? Do you have any questions? See,
No,
now
sir.
time is 12:35. I could find improvement in the attendance. It was, I think, 40, 41. So now another 5 people have joined. Huh? I can identify who have joined. Okay, so just don't join because of attendance, because you all know I take attendance at the end. So if you join just last 5-10 minutes, you will be able to finish your quota. Just if you are attending, if you are joining like that, so it won't give any meaning for your this one. That is why people don't respond when I ask some questions. Okay, even you are not ready to unmute and talk also to say yes or no. Just I think as far as my this one is concerned about, I wanted to tell today about the BPSK. What is BPSK and how do we represent the BPSK signal mathematically? See, one fellow has left. No, now it has become 48. So again, 3 more people have joined. So by the time I reach 12:45, so strength will become 55, like that. So people are playing, and when I ask questions, they don't. So now onwards, what I will do, for whoever questions I ask, if they answer, then only I will consider their attendance. Otherwise, I will not. Even if you are there from the beginning to end, I don't mind. And if you have joined now, and if you are answering, I don't mind. Okay. So if you are not unmuting and talking, I will not give attendance only. Just to check my understanding, let me ask some few questions. I think Rishav Kumar. Rishav Kumar. Yes, Rishav Kumar is there. No. So he's not responding, means he's the fellow who has joined now. Rishav Kumar. What about Rushang? When I was calling attendance, you don't have to answer, Rishabh. Rushank also not speaking, okay? No need to talk to me. Sovik Roy,
Yes, sir.
yeah. Can you just tell me how do we represent in case of BPSK the symbol one man mathematically? Sovik Roy. See, now the strength has become 49. Cleverly people are playing. Yes. So if you are not answering, your attendance will not be given, man. I clearly understand whether you are there from the beginning or not. If you are not able to reproduce what I said, there is no point in giving attendance. You have to be attentive. Yes, Arshata. Arshata. I will. Yes.
Yes,
If you are
sir.
not responding, yeah. Can you tell me what question I was asking to Sovik Roy?
Can you repeat, sir?
Why you did not hear? You should know. Why do I need to repeat? If you are there, if you are attentive, definitely you will be able to answer. No, what question I have asked to Sovik Roy? Okay, you tell me how do we represent uh, mathematically the BPSK signal for symbol 0? Yes, for symbol 0. So it shows we are not here. Yes, Rohit Joshi.
Yes, sir.
Yeah, can you tell me how do I take a decision in favor of symbol 1 as far as the receiver operation of BPSK is concerned? How do I take a decision in favor of symbol 0?
Yes, sir.
I'm asking.
Sir, threshold is 0, sir.
Uh, yeah, why threshold is 0, man? How do you say threshold is 0? On what basis you are setting the threshold value is 0, man, here? What is this, Rohit Joshi? See, I thought only 5 slides, man, 5 to 6 maximum. So people are not attentive, it shows. Yes, Rakshita W. I said no. Rakshita W. Yes, what about Pooja? Pooja. Okay, don't respond. So I will not give attendance. I will make absent. What about Neeraj? Neeraj.
Yes, sir.
What man? I should call thrice to talk to you. Hmm? What Neeraj?
So no, sir, I
Can you
was
tell?
there.
It was there. Okay, just can you tell me the working of BPSK receiver, man? Neeraj. Still, I shared the slide. Slide is there. It is very much visible for you. I think you should be able to say how the receiver will be able to estimate whether the transmitted symbol is 0 or 1. Yes, what happened to Neeraj?
Not sure, sir.
Not sure. Why you are not sure? Tell me, can you tell me the reason? Neeraj. Hey, talk to man. Talk to me. Yes.